When America was young, traveling was slow, uncomfortable, and dangerous. No one traveled much until steam engines began pulling trains in the 1830s. Locomotive technology advanced dramatically over the next 100 years as it played a central role in opening up and developing the vast open spaces of the United States. You could say America and her railroads grew up together. The haunting voice of the steam engines enchanted dreamers of every age. In the 1950s, a new era began for American railroading, an era of diesels and streamlined passenger trains. In a matter of years, the steam locomotive that had played such an important role in America's history had all but disappeared. Luckily, the great age of steam locomotion has been reborn with the construction of two beautiful locomotive replicas, the Jupiter and 119, located at the Golden Spike National Historic Site, Promontory, Utah. Over 100 years has passed since that famous spike of gold was driven and the pilots of the original locomotives touched, binding the nation with a ribbon of steel. Unfortunately, the remarkable significance of this historic event has been lost to America's younger generations. Determined to restore this historic event to its proper place in our modern perspective, the National Park Service initiated the project of building replicas of the two steam locomotives, the Jupiter and 119. Steam engines like these haven't been built in over 100 years. No blueprints or plans remained of the original engines, only photographs and a few technical specifications. In 1975, the National Park Service contracted O'Connor Engineering Laboratories in Costa Mesa, California, to build the replicas. Chadwell O'Connor, president of O'Connor Engineering Laboratories, and John Healy, his chief engineer, formed the team that were to draw the new plans and reconstruct the engines from the rails up.
One of the requirements in the specifications for the two locomotives was that they had to be within 1/4 of an inch of the original locomotives. This turned out to be a major problem in that there were no drawings on either locomotive. So the net end result is that we had to go back to photographs and rely on photographs almost 100% to get our information. And one of the things we did was to develop a micrometer. John Healy came up with one that would work with the calipers and a formula to change the dimensions from the photograph to the lineal dimensions as they would come out.
We had to design most of the components by scaling photographs. We'd established some basic benchmark dimensions like the center to center between the main driving wheels. Once this dimension was established, then other dimensions such as the diameter of the stack, the length of the steam chest lagging, the length of the headlight and the height of the headlight could be established.
We went back to get the basic dimensions from a few dimensions that we had. We had the diameter of the wheels, we had the gauge of the locomotives, and very fortunately we had a drawing of the boiler from one of the locomotives. And we found the serial number of the 119 on this boiler drawing, and that was sufficient to get us quite a few dimensions.
Bob Doty was one of the craftsmen working under John Healy from the beginning of this project. Today, he's the chief locomotive engineer for the Jupiter and 119 at Promontory Summit, Utah.
Well, the Jupiter and the 119 class locomotives represented state-of-the-art engineering in mid-19th century. They were American standard type, or 440, which meant they had 4 drivers coupled and a 4-wheeled engine truck under the cylinders to guide them around the curves, and of course no trailing truck underneath the boiler.
To accommodate the construction of the steam engines, the O'Connor shops had to be re-outfitted. Concrete floors were removed and track was installed. Truckloads of ballast or gravel were hauled in and tamped to anchor the ties. While the shop was being outfitted, the drawings were being made.
We set up a procedure where John Healy and myself supervised all the drawings. We ended up with well over 700 drawings on the two locomotives. One of the drawings that we made on the locomotive, in fact it was the drawing for the cylinders, which I made myself, is 22 feet long, and everyone in our drafting room kidded me about having such a long drawing, but it came out well and the cylinders worked, so I guess it was all right.
Once the drawings were completed, the frames of the Jupiter and the 119 were torch cut and machined at L&F Industries in Los Angeles. Cut from 4-inch slabs of solid steel with a cutting torch, the pantograph arrangement allowed the machinist to cut directly from the drawings of the frames. By cutting from one single plate of steel, the frames would be stronger than the originals. The boilers on the Jupiter and 119 were built by Dixon Boiler Works in Los Angeles. Since both boiler shells had the same 50-inch outside diameter and the same number of 2-inch flues, they looked identical from a distance, except for the extended smoke box on the 119.
Well, the original boilers on the Jupiter and the 119, which was state-of-the-art at that period of time, were made out of wrought iron, which was an iron similar to cast iron that was worked to make it supple and malleable. And they used to form the sheets on a drop hammer and make them into the shape, and then they would rivet them all together and caulk the seams with a caulking chisel to make them watertight. But the problem with the old wrought iron boilers is that they incorporated a flaw in the sheet in forming those sheets with a drop hammer. They may never know it until the boiler blew up.
Today, the seams of the Jupiter and the 119 are electrically welded to increase the boiler's strength and improve safety. Each boiler is licensed for 160 pounds of steam pressure under the ASME code, as compared with 120 pounds of pressure on the original engines. A huge boring drill using a 2 1/32 inch bit was used to drill the holes for the fire tubes, which run the length of the boiler. This process must be precise, so when the fire tubes are rolled into place, there will be no leaking.
The biggest single casting on the locomotive, and probably the most difficult, was the main cylinders for both locomotives, because they have a lot of passages for the steam and the exhaust and so on.
Well, the cylinders were all cast in one piece, kind of a different method. The original ones were cast in 3 pieces and then bolted together, but Chad didn't like that idea because they were famous for falling apart. The bolts would come loose, so he designed it to be cast in one piece.
Cores were used in the casting to leave the cavities for the bore valve ports, steam, and exhaust passages. This alleviates the need for the expensive and time-consuming process of machining the holes after the cast is made. The cores were made of core sand, a sand blended with oil and baked to harden, so they could be easily removed with an air hammer after the casting was completed. This casting weighed about 5 tons in its rough state and was cast in gray iron.
These cylinders, after they were cast, they had to be put on a big boring mill, and all the steam passages in the valve portion up in the steam chest here all had to be machined very precisely.
Well, another friend of mine that worked at Disney, Maury Hauser, was an excellent engineer, and we had him come over on weekends and work on the valve gear. And when we put them together, we left a key loose that could be adjusted in case they weren't timed just right. But as it turned out, the timing was perfect, and I think on one locomotive it was within 7 thousandths and the other within 15 thousandths, and that's closer than the original manufacturers ever got on their valve gear, so we were just tickled to death with the drawings on that.
On early locomotives, the frames were bolted to the cylinders and would eventually vibrate loose. Chad O'Connor decided to shrink fit the frame to the cylinders on these replicas to correct this problem. The frame was dropped beneath the cylinders and heated with a large acetylene torch until they expanded a 1/16 to an 1/8 inch beyond the size of the cylinder mounts. The frame was then jacked up to fit the cylinder mounts and allowed to cool. This heat shrink process assures a lasting fit. As an extra precaution, the cylinders were bolted to the frame.
Wheels on the locomotive have to look well. They have to have good appearance, they have to balance, and they have to be concentric. It's very, very important to have top-notch castings on the two wheels, and to boot, they're quite large in diameter. But very fortunately, we had a good pattern maker, and they came out very well.
The wheels on these locomotives are about the largest parts that you will find that were cast, and they were cast in manganese steel.
The patterns for casting the driving wheels were made of pine or gelutong wood in two pieces, the inside and outside patterns. The patterns were then placed in a mold flask, covered with talcum or parting compound, and then oiled sand was rammed securely around the mold. Cores were used because of the necessity of the casting of the holes for the drive pins and the wheel axles. After the sand was rammed firmly in place, the pattern was then removed. Both halves of the mold flask were joined, forming the hollow cavity, which is ready to be poured with manganese steel.
After the casting had cooled, they took the wheels out, they were machined to about this diameter right here. Now you'll notice that it has a tire on there. This is known as a driving wheel center, and this is known as the tire. The tire is made of steel. It was machined, probably for maybe a 62,000 shrink fit, something like that. And then it was put in what is known as a fire ring. And there were flames about every 4 inches all the way around that tire. It was expanded so that it would fit loosely over the wheel center, and then with a crane and a clamp, it was lifted onto that wheel and jigged on and allowed to cool. Now, when that tire cooled, it shrunk to fit that wheel in such a manner that it'll never come loose. And so that is something that is almost a lost art in the locomotive construction field.
These huge drivers then had to be machined on a wheel lathe, a one-of-a-kind lathe large enough to accept the drivers. The truck and tender wheels were mounted on another lathe and trued up so the wheels would ride the rail in balance. The axle pins, first coated with white lead for lubrication, were pressed into the driving wheel centers under 50,000 pounds of pressure. The driving wheels were similarly pressed onto the axles. The frames were placed on blocks and readied for the driving wheel and axle installation. The large driving wheels and axles were now ready to be attached to the frame. The axles have a driving box on each end next to the wheels containing a half bearing known as the crown brass. This allows the driving box to move freely up and down within the frame, held in place by the weight of the engine. These bearings were all machined and installed on the axles before they were to be mounted to the frames.
Yeah, it looks nice and even now.
After the boilers arrived from Dixon Boiler Works, each were lifted by a large gantry crane and attached to the frame.
When the boiler was assembled to the main cylinder casting and the dry pipe, the main steam valve, the steam dome cover, the throttle valve, and all the other pressure part closures were installed, we used our house boiler to charge up the locomotive boiler and then open the main throttle. This blew the material, the construction debris, the dirt, the sand, and the other things that may damage the cylinder and the piston and the other moving parts. And we continued to do it until we had a clean plume of steam.
Well, after the boilers were firmly attached to the frames and the cylinder saddle, we had to insulate the boilers. Now, these boilers are insulated with 1.5 inches of calcium silicate block, and they come in 3-foot sections, about 8 inches wide and 1.5 inches thick. They're laid on the boiler, and then they're wired on, and after they're wired on, a man comes around with what is known as mud. It's an insulating compound, and he smears that all over to kind of smooth out the rough edges and to fill in any little holes that might still be there in the insulation. Interestingly enough, the original locomotives were insulated with white pine, and that was about the only insulation they knew of at that time. And of course, over a period of time, it would burn and char and become useless.
Since both locomotives were made by different manufacturers, this produced a lot more work for us because different manufacturers had different techniques. So we ended up having to make almost all the parts ourselves, with the exception of a few nuts and bolts and screws. Every part was unique that we made.
Some of the last pieces constructed for the engines were the most beautiful. For example, the cabs for both locomotives were made of wood by master carpenters Wayne Helmick and Buck Marin on the floor of the O'Connor shops. The workmanship was so outstanding, it was decided the cabs would be left unpainted. Instead, they were stained so the natural beauty of the wood could show through. The complicated job of building the pilot was tackled by Buck Marin.
Well, these cowcatchers, or as they're technically known, pilots, were built out of solid oak with steel beams or steel frames. Of course, originally they were designed to throw cattle or buffalo off the track, especially coming through the prairies of Nebraska, where they had the thousands of buffalo roaming free. Well, the bells were quite a unique project because we wanted them to sound right. A lot of the later locomotive bells were pretty clangy. We wanted them to have a nice, pure tone.
The recreation of the bells for the Jupiter and the 119 was a combination of artistry and craftsmanship performed by the Aspeita brothers in their Bay City foundry in Wilmington, California. The bells were laid out to a formula for curvature and thickness used in the 1860s.
After we got the bells, we tuned them by having them machined until they were just exactly the way we wanted them, and we think we've got some pretty sweet sounding bells on these locomotives.
Finally, the brass fittings were installed. The gleaming brass is part of the mystique of these locomotives. Finally, the day arrived, the Jupiter's first major test. With Chad O'Connor at the controls, the engine was put under steam and backed from the shops. The success of this step marked an historic achievement in recreating the industrial technology of a bygone era.
One of the most important steps to completing the locomotive is the finish. Without a good finish, of course, all the work that we've done on the rest of the locomotive would be lost. What we did, since no one within the plant was any good at artwork or painting, that sort of thing, we got an old friend of mine, Ward Kimball, who was one of the first 6 people that started the Disney company, one of the animators. And he did all the artwork on the paintings on the corner, on the back of the tender, and the numbers on the sides of the cab, and other painting around the locomotive.
He painted the left-hand side of the sand dome of the 119 as it was represented originally as probably Johnny Appleseed. One interesting part about the sand dome, the right-hand side always had a bunch of soldiers or people standing there when Russell took his famous photographs, and so we didn't really know what the sand dome looked like on the right-hand sides.
Ward solved the problem by studying history books and finally decided on the mountain man, Jim Bridger, as an appropriate character to paint on the right-hand side of the steam dome. A couple of the people he brought out from Disney did all the gold leaf work. Now, we could have gotten by with gold paint, but we decided to do the job a little bit on the extra side, and it was a bit of a labor of love almost throughout the whole job.
Mr. Kimball also etched antique numbers and letters of the 1860s on the faces of the steam gauges and boiler water glasses, which were nearly the only commercial products on the engines. On April 30th, 1979, the Jupiter and the 119 were ready to be shipped to their final destination at Promontory Summit, Utah, 800 miles from the O'Connor Laboratories in Costa Mesa.
The two locomotives were delivered about 10 days ahead of the final date, which was May 10th for the celebration. And we were quite surprised at the number of people that were present.
Several days later, a ceremony was held so that the general public could see the locomotives. The locomotives were christened with water from the Atlantic and the Pacific Oceans to signify the union of the coasts with a continuous ribbon of steel. Today, during the summer months, the Jupiter and the 119 can be seen daily at their permanent home at the Golden Spike National Historic Site, Promontory, Utah.
These locomotives represent the finest products of 19th century engineering. They are as beautiful now as they were over 100 years ago. I hope today, as people look at these engines, they will reflect upon the historical heritage they represent.
Look back on the work that we did on the two locomotives, and frankly, I wouldn't trade it for any other thing that I've ever done in my entire life. They both came out beautifully. They're both running well. They've had little or no problems and very, very little maintenance.
Several times each year, the trains are used in a reenactment of the Golden Spike ceremony, commemorating the meeting of the rails in 1869.
The last spike is a regular iron railroad spike that can be driven with the maul. Now, both the maul and the spike are wired to the transcontinental telegraph line so that the entire nation may hear the blows as the spike is driven. Just ring. Oh, goodness. We missed. Would you care to do the honors of Dr. Grant?
Thank you very much.
Embarrassing.
Here, would you do this, sir?
You've been doing the work anyway. Hip, hip,
Bret Hart captured the moment in words. What was it the engine said? Pilots touching head to head, facing on the single track, half a world behind each back.